Hey guys, just want to go through the centripetal forces worksheet, give you a little bit of extra help in case you need it. But I really suggest that you try to do this on your own first, and then use this only as a guide. So, we're trying to solve number one, a 20-gram ball. You can read it. And a couple things. First of all, that's not what I want to do. The mass of the ball is given in 20 grams, but we need it to be in kilograms. So I know that there's 1 kilogram has 1,000 grams, so that tells me that my mass is 0.02 kilograms. Secondly, just looking at my radius, I know it's 60 centimeters. I need that to be in meters. So I know that 1 meter has 100 centimeters, so that means that my radius is 0.6 meters. And then my 80 times per minute is times per minute. That is, times is kind of a revolutions, so this is ultimately going to get into radians per second, which means that it is a omega, but I've got to convert. So 80 times means 80 rotations, or revolutions, and this one's kind of ambiguous. Rotations per minute. I've got to get rid of the rotations to make it 1 rotation per 2 pi radians. Rotations cancel. And I've got to get 1 minute is 60 seconds, which tells me 80 times 2 pi divided by 60, 8.38. This is an omega, so that has units of radians per second. Just going to break away for a second and say a couple units that are important. Omega is always in the terms of rotations per time, whether it's minutes, hours, seconds, or whatever. It could also be revolutions per minute is a common unit, but it's not really, because you've got to turn this into radians per second. So if you see something along this side, along these lines, where you have excuse me, number of spins per minute or number of turns per hour, or whatever the case is, that's telling you that it's an omega. If you see meters per second, or you see the word speed, that's telling you that that is a tangential velocity. So just going to be very careful with the units for this. So we got to find the angular speed. Well, angular speed is omega. So I have done that with omega for part A. Omega equals 8.38 radians per second. Part B, I have to find the force. Well, the centripetal force from the notes is m omega squared times r. So I just have to multiply the 0.02 times my omega squared, 8.38 squared, times 0.6. And I get 0.84 newtons. Alright, so hopefully that helps with question 1. Question 2 is using the same ball, but except now it's in a vertical motion. So the ball is in the string, and we're going to look at 2 spots. One is at the top, and it's when it's at the bottom. So at the top, there's 2 forces. So this is a top free body diagram. There's 2 forces pulling down. There's the force of gravity helping, and there's the force of tension pulling down. One of these is ultimately providing the centripetal acceleration. That's the thing that's actually attached to it. So there's a centripetal acceleration and centripetal force, and we know that that centripetal force, Fc, has to be 8.38 newtons, and that was from the previous. So the centripetal force is like the net force acting down toward the center, and in this case we know that the centripetal force comes from the tension because it's attached directly to the rope. So my centripetal force, we want to find what the tension force is. My centripetal force, which is the net center seeking, is equal to, since the centripetal force is acting to the center, my centripetal force is acting that way. My centripetal force is the sum, gravity's helping pull me to the center, plus the tension force. We're ultimately trying to find this. So I know my centripetal force is 8.38 newtons, and I know that my force of gravity is, let's do it up here, my mass times my acceleration due to gravity, which is 0.02 times 9.8, which is 0.196 newtons, equals 0.196 newtons plus Ft. And really I could have all of these as negative, but if they're all negative, they cancel out anyway. So I can just make it positive, just to make the math a little easier to see. I want to solve for the tension force, because that's what it's asking. What is the tension force in the string? So I subtract 0.196 from both sides. 0.196. And 8.38 minus 0.196 gives me a tension force at the top. See, at the top of 8.18 newtons. But that's at the top. At the bottom, it's a little different because my tension force has to pull up, and so does my net centripetal force is upwards. But I have force of gravity that's pulling me down. So the equation that I had up here is a little different. My centripetal force is up, so that's a positive number, equals my tension force, which is up, that's a positive number, minus my force of gravity. So, in this case, because force of gravity is down, in this case, my centripetal force is 8.38. Trying to find my tension force minus the force of gravity. Well, it's the same thing. Mass times gravity hasn't changed. So that's still 0.196. But because it's minus here, now I have to add it. 196.196. So my tension force, just coming up here, is going to be 8.38 plus 0.196, which, just keeping a couple extra decimals, is 8.576, or 8.58 newtons. It increases a little bit. So this one was 8.18, sorry, it wasn't written very nicely, 8.18 newtons. When you're at the top, when you're at the bottom, it's increasing because you have to overcome gravity. So to overcome gravity, you have to push harder, you have to pull harder. So this rope is more likely to break. This might be a future question in the on a quiz or whatever. When is it more likely to break or most likely to break? It's most likely to break at the bottom because of this reason. The tension force or spring force or whatever force you're dealing with has to be biggest at the bottom because it has to most directly overcome gravity. So hopefully you can see that and that works. Question 3, I think, is relatively simple. All you have to do is just change kilometers per hour to meters per second. But I think that question's not too bad. And question 4 is similar to the sample problem we did. So I will leave that for you to try and work through. And then centripetal forces worksheet number 2, I also would like you to do. And just do your best. I will check those on Monday when I come back. And we will begin the circular motion review in class on Monday. Alright, so I thank you, and again, have a good weekend, and I will see you Monday.